Right. So this microwave radiation has a spectacular spectrum. The curve is not a fit to the data. It is a black body curve of 2.73 degrees that fits the data unbelievably well. The error bars on the data points are really tiny, and it's amazing. In the 60s, when people tried to measure the spectrum, they kept getting observations that didn't agree very well. The techniques for measuring it just weren't ready. But they tried it. Okay, now this radiation is the same as a 3,000 degree object, except it's redshifted. Now we say 3,000 degrees because it has been a long time since the material, since it interacted with anything. If it interacts at a 3,000 and then the universe expands a lot, we know how it redshifts. Just like anything else. Photons are in free and they redshift as the universe expands. This is expanded. Well, it was 3,000 that interacted. And basically the radiation back at a redshift of 1,000 or so, the radiation looked like the surface of a red giant star. It was hot. 3,000 degrees is pretty hot. And the universe, it showed that. The universe has expanded 1,000 times. Cosmological redshift, turn the radiation into microwaves. That was the amazing finding. All right. This has been predicted by theory. People had predicted it since the 1940s. And they looked for it. They thought it would be a higher temperature. They never found it. The techniques for finding it were not very good. But it comes. Now, the point is that this radiation comes from everywhere. Everywhere you look, you see this radiation beaming at you. The whole sky radiates. And it's a perfect, just about a perfect black body. And the question is why? What does this tell us about the universe? It's very significant. All right, we'll talk about that today. All right, here, now, if you look at the first time there was a satellite called the Cosmic Background, CMB, Cosmic Background, no. This is Cosmic Background Radiation. Okay, and this is now radiation that has been processed, at which they throw away, in this picture, they throw away all but one part in 10 to the fifth. It is completely smooth down to a level of a part in 10 to the fifth. So they just remove it from this picture. And that was, this is the picture again. This is with 7-degree resolution beam, pretty poor. If you run a higher beam sample on it, this is just 20 arc minutes, you get incredible structure. What does this structure tell us is a fundamental question. What does this mean? It's a very small fluctuation on the microwave radiation, a part in 10 to the fifth. What does it tell us? All right, now this has been a subject of tremendous debate in the 1960s and 70s. It tells us something incredible. So let me tell you about it. All right, the curve of the fluctuations, let me go back. The fluctuations here have a, if you take a spectrum of them, a spatial spectrum of them, you take, the next picture shows the fluctuations that you see. Fluctuations have a peak at about 1 degree. What does that peak mean? Let's look at this. 1 degree peak is about the size of one of these blue or white structures. Okay, so there are peaks there. And it has a lot of structure on bigger angle. Here's a hole, here's a positive region. And the question is why? This is not a random distribution. And the question is why? Why does it look this way? And it has this spectrum. A random distribution will be perfectly flat across this this drawing. I mean, it would be just flat at some level. That would be what's called Poisson noise. And that obviously is not what we see. The structure this is a theory. The line is a theory called lambda cold dark matter. And fitting the theory obviously is a good fit to the data. All right, now what do we learn from that? All right, the theory is rather good. All right, now let's go on and we'll see. The most distant galaxies come from when the universe is a few billion years old, as we've seen, but the radiation prevents us from seeing the universe before the temperature, before the age of the universe was 380,000 years. Now, what does that mean? At that point, the temperature is high enough to ionize the electrons from the neutral atoms. So instead of having atoms of hydrogen, for example, you have electron-positron soup. It just churns it into a radiation, a plasma. And the photons interact with they scatter off the electrons. Now, scattering off the electrons is just like a shower glass door. A shower glass door is very milky. You look through it, you can see the light, but you can't see the definition of what it is behind it. That's what a shower glass will do for you. This is exactly the same as what happened to the radiation. It is being scattered by the photons, by the stuff. All right, now how do we know that anything I'm saying is at all right? And we know because the conditions and expansion of the universe are well known today, and running it backward, you can learn the temperature of the universe at any epoch. Now, the temperature of the universe turns out to go, the temperature goes as 2.7 degrees times 1 plus z in Kelvin. Now, that means at a redshift of 0, the temperature is 2.7 degrees. At a redshift of 1,000, the redshift is, the temperature is 2,700 degrees. At a redshift of 1,000,000, it is very high, very low. So here, I'm going to plot the temperature of the universe. This thing's getting faint again. Anyhow, temperature of the universe gets up to crazy temperatures, 10 to the 32 degrees Kelvin. The highest temperature we saw in a star was only 10 to 12 degrees Kelvin, which is pretty hot right there, but that's over here. And that is occurring in the universe when it was 10 to the minus 5th or 10 to the minus 7th seconds. If you want to see the universe, even hotter, then just look at it earlier. Now, this is well known to physicists and astronomers, and because of this, the universe is incredibly hot, and it is something we can use. Now, what happens is the following. We have the equation E equals mc squared. So the temperature is a measure of the energy the particle has of random motion. That's an energy. So that means that in that situation, you can have mass convert straight to energy, energy convert to mass. It goes back and forth. And that means that the temperature is greater than 10 to the 12th degrees, greater than seen in the center of a star, you can have a photon here collide with another photon, and out come electrons and anti-electrons, matter and antimatter. If the temperature gets hotter, you can have them make protons and antiprotons, or neutrons and antineutrons. In other words, if the temperature gets hot enough, the radiation has these collisions, and the collisions will make anything you want. Anything is made there. Absolutely everything that's possible will be made. All right. So the destruction of matter. two particles, when they collide, they annihilate and form gamma rays. That's what Einstein's equation tells us. And the first moments of the universe, they continuously are converting into each other. The mass energy of the universe is unchanged by this reaction. It's just, it's such high temperature, you can't believe it. All right. Now, what is happening? The universe, oh boy, this thing is faint. Can you still see this? The dot? Oh, well, I can't see it at all. So, all right. The universe is, I'd only see it for a moment. All right, the universe is cold here and very hot down here. Incredibly hot. Hot enough to easily exceed the energies that are reached by the biggest particle accelerators built on the Earth. The LHC is the biggest particle accelerator. That's the one in Europe. It exceeds that incredibly fast. It does not take long. That LHC will get to, it'll get back to the temperature of that was present at 1,000th of a second, 1 millisecond or so, or 10 to the minus 10 seconds, I'm sorry. Okay. All right. I forgot to plug it in. Anyhow, the universe starts off with a bang. What do we mean by this bang? Wait till I'll tell you what the bang, what it really was on a week from today. Okay, I'll talk again about the Big Bang. All right. The universe was in something called the Planck era. And it lasts very short time, 10 to the minus 43 seconds. And remember, I've told you we had trouble linking quantum mechanics with the theory of gravity. We just don't seem to be able to do it. And in this area, we apparently get in the epoch is so hot that we actually get to the string era. The string era, where the dimensionality of everything goes up. We'll talk more about that. But instead of it being a four-dimensional object in space, everything in space is 11-dimensional, 10-dimensional. And we'll talk about that. This theory is considered very promising because it is the first and only theory we've seen that can unify quantum mechanics with general relativity. For that reason, it's taken very, very seriously by the physics community. Okay, so we don't know what happened then. It's too far away from us. We can't describe it. And we can still talk about the universe at 10 to the minus 43 seconds, sort of. But you can't talk about the universe earlier. You can't talk about the actual explosion or whatever the hell happened. Not yet. Wait till Tuesday, and I'll show you a way that we can talk about it. Okay, but what actually happened was the forces of everything were unified. That is something. Remember, this unification is the grand unification has to unify gravity with the grand unified theory, and that is, we think, occurring at a temperature at a time of 10 to the minus 43 seconds. That is such a short time. The time it takes photon to cross the nucleus of a proton, for example, is 10 to the minus 23 seconds. 10 to the minus 23 is a hell of a lot larger number than 10 to the minus 43. It's a ridiculous number. It's so small I can't talk about it very much. But the energy is known as inflation, and we'll talk about why that is. Here's what I mean by unified theory. If you plot the relative strength of everything on one plot as a function of temperature or function of energy of the particles, the energy per particle is such that gravity is incredibly weak, just incredibly weak. Electromagnetism unifies with the weak force we know that works at something called the electroweak scale. That was discovered by Stephen Weinberg and Sheldon Glashow and Abdus Salam in the 1970s. All right, and that was a big breakthrough because that was a breakthrough as powerful as Maxwell's unification of electricity with magnetism. That was a big deal. All right, but it has only two of the forces. The strong force will unify in terms of something called a gut force, grand unified theory. And they've got models of this, and the grand unified theory works to describe everything, except gravity. And the only time gravity looks as though it unifies with the forces at a temperature, it's ridiculous. 10 to 33 degrees or so. It's too much. All right, the universe at a temperature of 10 to the minus 10th degrees, the universe is 10 to the minus 10 seconds. It's cooled down to 10 to the 15th degrees Kelvin. The electromagnetic force separates at that point. Okay, and this not only was theoretically discovered, but it was experimentally discovered in 1983. They saw particles, crazy particles, and the particles are predicted to exist in nature at temperatures greater than 10 to the 15th degrees. This is something we can reach with our particle accelerators. We reach to about here. Okay, so the particles below that temperature are all distinct, 4 different forces. They're as numerous as photons. Now, when the universe was 10 to the minus 4th seconds, the quarks combined. The quarks make up the center of a proton. 3 quarks merge to make a proton, and they seem to make everything. Okay, at 10 to the minus 10 seconds, 10 to the minus 3 seconds, the universe cools to 10 to the 12th degrees. And here you've got everything annihilates. Now what's happened is that, oops, sorry. All right, at this temperature, the electrons and positrons are still created by the gamma rays. They can collide and make an electron and positron. And they do, all the way. Now, all right, so we've taken the theory from 10 to the minus 40 seconds all the way up to here, 10 to the minus 10 seconds. All right, now what happens at this point? The universe still has a number of stages to go through. And this is an important point. This is the era of nucleosynthesis. What do we mean by that? You've got, in this universe, at this temperature, the neutrons and protons are free particles. They're just flying around. And, of course, neutrons and protons, if they hit each other and stick, what is that? That's deuterium. So they're making deuterium. And then the deuterium collides with something else, and it breaks up. All right? All right, so now, when the universe is 10 to the 9th degrees, the temperature is too low to allow this merging of protons and neutrons. And all of the making of heavy elements by those collisions stops. Heavy elements means things heavier than free neutrons, free protons. So everything is made at that point. And what is made? At this point, it has made 75% of the nucleus, just a bare proton, but 25% is helium. Helium nuclei are made in abundance at this epoch. And there's a little bit of deuterium made, and lithium. These are important tracers. Deuterium is in the water. It's in the water around us, and it's a trace element in the water. It's abundant. It's seen at a level of 10 to the minus fifth per cubic. The ratio of deuterium to hydrogen atoms is 1 part in 10 to the fifth. Now, what does that mean? Where was this deuterium made? It was not made in stars. Deuterium is too fragile to make in stars. And all the deuterium was made in the Big Bang in the first 3 minutes of the universe. Now that is crazy to say that, but it is what people believe, and they've worked out mathematical models that show it actually did, at that point, it did form deuterium. Okay, all deuterium in our oceans was made in the first 3 minutes of the universe. That is crazy. Most of the helium was made at the same time. The stars make helium. We've talked about the stars making helium, but it turned out that the stars most of the helium in the universe is not made by stars. Most of it's made in the Big Bang at this early epoch. Now this is incredible evidence for the Big Bang model, because it shows mathematically, people calculate all this stuff, and it shows that the Big Bang predictions are exactly what people see. That's why scientists believe in something like crazy as the Big Bang. It's not because they just made it up. There's real data to support it. And the strongest source of the data is this deuterium abundance, because it cannot be made in stars. It's too fragile. All deuterium in stars is burned up as the star is just forming from a primordial gas cloud. Okay, so all right, so from 3 minutes to 10 to the 5th seconds, 10 to the 5th years, the universe is just a hot plasma. A plasma means it's charged, electrons and protons. The plasma is what is everything. The plasma and the photons bounce off the electrons to electrons. The photons don't travel very far because they're constantly scattering off the free electrons. And the universe is very, very opaque. And when it's down to 380,000 years, the universe has cooled to a temperature of about 3,000 degrees. And using just the same equations that chemists use, the Saha equation. Does anybody know what the Saha equation is? Anybody study this in chemistry? All right, well, it is something you use to calculate the abundances of elements in any situation. The universe has cooled, and as soon as the universe takes up the electrons, as soon as they combine with the protons, the radiation is free. The radiation had been trapped by the electrons, but suddenly it's free. And this is at a period when the redshift is about 1,000 or so, 1,200, and the temperature and the time of the redshift, this is about 380,000 years, and then suddenly the radiation is free. And that radiation escapes and travels the entire universe until it hits us, and we detect it. The radiation just keeps going. There's nothing to prevent it from traveling forever. The universe is transparent from that point on. So what's happening is the universe is incredibly transparent. If you look at the universe, photons come down, or here. Photons are trapped in here, and they're bouncing. That's the wiggly lines. They're bouncing, bouncing, bouncing. and then suddenly they are free at that point. Okay, you can see back as far as that. You can see to where the redshift is 1300 is the real number, and the atoms are ionized. So it's incredible to think how far we can see the universe. All right. And these microwave radiation photons, the cosmic background radiation, it's scattered for a while, but now it is free. And the photons travel forever. All right, so this is known, this era right here is known as the decoupling era because the photons are decoupled from the matter. The decoupled era. That's the edge of the visible universe. The microwave radiation comes to us without interaction, and that means that you can't see beyond it, but that's as far as you can see anything. So they're part of what we call the visible universe, although it's not really visible light. And we can see all the way back there. Okay. All right, and the microwave radiation is also a relic of the Big Bang. We see it because it's there. What does it mean? Another relic was the abundance of light elements, deuterium, helium, lithium. And this relic, you may say 2.7 degrees, that's negligible temperature. It's nothing. But it is very hot temperature because if the temperature is at 2.7 degrees, it turns out the density of those photons C is about 100 or 200 photons per cubic centimeter. And the number of protons in the universe is 10 to the minus 6 per cubic centimeter. That means that the photon to proton ratio is a huge number, like 10 to the 9th. 10 to the 9th is the ratio of photons to atoms in the universe. And the question is why? Why isn't it, say, a sensible number like 1 or 10 or 50? Couldn't it have been a different number? And why has it come out to be such an outrageous number? All right, so we'll talk about that. The universe at this point is filled with gas, sometimes called the dark ages because there are no stars in it yet. Density enhancements in the gas and gravitation are attracted to each other, and they form they form clouds and the first stars. Okay, and then later, after 10 to the 9th years, we come to the era of galaxies. Okay. All right, the first galaxies came into existence about a billion years after we start counting. And that's what we call the current epoch of the universe. 10 to the 9th years to 10 to the 10th years is the epoch of galaxy formation. All right, this is the epoch of galaxy formation. This is a picture taken of the universe as far back as you can. This is a long exposure taken with the Hubble Space Telescope. These objects, these little blips, are pieces of galaxies at redshift 3 and 4. They're all very, very distant. That means their travel time to get to us has been 10 billion years. Okay, they are old, very old. Okay, now here's a paradox for you. If the sky, here's a puzzle. If the sky is infinite in extent, then why isn't everything bright? Why can we see all these spaces between objects, between stars and galaxies? Why is the sky black, in other words? Why is it black? And this is known as, eventually we should see a star. And this is known, this whole thing, and is known as Olbers paradox. Now, what am I talking about? In Newton's day, Newton postulated that his theory of gravity worked on all scales. But if you wanted to keep the universe static, you merely had to make it larger. Here's his universe, and if you make it larger and larger and larger, eventually the universe, all this out here, attracts this matter and prevents it from collapsing. In order for that to work, it really has to go out an infinite extent, way out here. And then you say, well, let's see, if I draw a beam out about here, eventually every beam is going to intersect a star. And that when it intersects a star, you say, well, it's going to be, it's going to come back, it's going to have the brightness of a star, which is not very black. It's very bright. Now, you might say, wait a minute, these stars are far away. They're far away, and the luminosity goes as 1 over r squared. All right? But the number of stars varies as r squared. Exactly opposite this. And the number of stars times the luminosity is independent of distance. That means you have a equal probability of having your beam collide with a star anywhere. And so Newton didn't realize when he made his conjecture that the universe being infinite, which he said, would make it hard to have the you can't have this you cannot have the universe be infinite in extent. And the paradox was known at a time. Wait a second. All right. It was known as Olbers paradox. That's all right. Now, the issue is, how can you solve this problem? How can you solve this problem? And Newton didn't think of this, but other people did. In the universe, we know that these shells have a different look-back time. Say this shell has a look-back time of, say this time is, say, 13 point, whatever the hell it is, 6 or 3, what's the age of the universe? 7? Okay, 13.7 billion years. That means that a beam can just go to here. It can't go further because it travels at a finite speed. In Newton's idea, he wasn't thinking of the speed of light. It just went forever. But here you can only go a certain amount. And the expanding universe makes it dilute as well. The expanding universe takes it from visible light to infrared light. So that's shifted as well. So there's plenty of reason why in an expanding universe the sky is not infinitely bright. But you think about it, you'd think in Newton's idea the sky should be infinitely bright, and it's not. Okay. Now, if we talk about a model, we want to ask, what is there that verifies the Big Bang models? All right, the Big Bang models make some predictions, and they've been incredibly verified. The existence and characteristics of microwave radiation and the heavy elements are the elements in the early universe. These are two predictions that the Big Bang models predict. There is no other way to explain the microwave radiation and the helium abundance. That is how they are all made in the Big Bang, and it perfectly explains it. So if somebody asks, oh, Big Bang, just another theory, it's a lot of crap. It is not a lot of crap. It really works. It really works. So scientists know what they're talking about when they say the Big Bang theory. It works at least to a time of 10 to the minus 3 seconds. Anybody challenge the theory beyond that? Okay, go ahead. But I'm telling you that the whole Big Bang model, it definitely works at that age. Okay, it agrees incredibly well with current observations. It is just spectacular agreement. Now, the microwave radiation. The sky, here is the sky. At original sky, this is the sky that Penzias and Wilson saw. Exactly the same temperature anywhere. And if you take the radiation and subtract a part in 1,000 off this here in a place you can't see it, but just part 1,000, 2.73 degrees is the original temperature. And now we have a scale at which the temperature is 3 10 to the minus 3 degrees is millikelvin instead of degrees. So it's 1,000 times weaker, and this radiation has a dipole pattern. What makes a dipole is our motion in space. If you're moving toward the light, it gets blue shifted. If you're moving away from the light, it gets red shifted. And you produce a pattern just like this. Does this mean anything? How much velocity are we moving at? And it is pretty incredible. Now, if you subtract the radiation to part in 10 to the 5th, you see the plane in the middle is the galactic plane. Lots of emission from the galactic plane. But up above and below it is the microwave radiation. This was first seen in 1990. Picture just like this. Okay. All right. So the microwave is precisely is uniform. That's one thing we learned. It took 10 years of searching for these deviations from isotropy. A lot of that work was done here. Berkeley especially did a experiment that they flew a U-2 airplane. They put the instrument in a U-2 airplane. Does anybody know what a U-2 is for? Anybody heard of a U-2 airplane? Oh, they're so young. U-2 is an airplane that was built for the military. It is a plane that there's some in California somewhere. It is capable of flying at I think 60,000 or 70,000 feet. Now you remember that commercial airliners can fly at 40,000 feet if they're lucky. This thing flies really high. It flies higher than the Soviet Union's anti-aircraft missiles. And that's why we built it, because we wanted to spy on the Soviet Union. And we flew these planes over the Soviet Union all the time. The Soviet Union knew about them and was trying to shoot them down and couldn't. And these planes took photographs of things, and we, in our paranoia, had to be sure that the Soviet Union was not cheating on any peace initiatives. All right, so then there was this incident where one of these U-2s ran into trouble, and they could not stay up at altitude. He had to descend otherwise the plane was going to blow up. And he descended and was shot down. The Soviet Union made a big splash about this. It was in the New York Times. It was a big splash. What year was that? Middle 60s? I think something about middle 60s. You guys weren't born. I know. Hard to believe. Huh? I think that's sometime in that period. All right, but the U-2 later, because it flies high and it flies quietly and it's above the atmosphere, it was really ideal for these experiments, and Berkeley used them, all right, and did a lot of experiments with them. Also, the group at Princeton tried to study this. But they had to fight the sky all the time, and they just were, it's a real pain in the ass to try to study the fluctuations. So they lobbied Congress, or they lobbied NASA all the time to put up a satellite. And eventually NASA relented, and they flew the COBE satellite, which flew in the 1990s. All right? And that's what gave us the first magnificent pictures. Okay. Now, the dipole isotropy. The dipole isotropy is interpreted as a temperature, a Doppler effect, and you can interpret it as the motion of the observer. And the observer, in this case, is measured at a part in 1,000, and you conclude from this that the Milky Way and the Andromeda Galaxy together are falling in the universe at 600 kilometers per second. 600 kilometers a second is a hell of a lot larger than the 30 kilometers a second we are moving around the sun. And the entire galaxy is only orbiting at 200 kilometers a second, 250. But the entire shebang is moving. And the question is why? A lot of my research addressed this question. We're not going to talk about it, but what it said was that the microwave radiation is the preferred frame because that's the frame where the only frame that does not have this dipole anisotropy in it. So, all right. Anyhow, that's an aside. We can skip that. All right. The COBE satellite was launched in '89, and for 4 years it collected data, and it produced a magnificent pictures that I showed you already. All right, now it resulted in these detection of fluctuations at a part in 10 to the 5th. They would not have seen these fluctuations in the first experiments that said the temperature is the same everywhere. But the fluctuations were there, and they're very weak. What do they mean? All right, the WMAP satellite was flown later in 2003, a decade later, and it had much better resolution. It was the first satellite, and this is the satellite that gave us these magnificent maps of the sky. Now, these peaks and valleys are very small. All right, and the question is, what does this imply? What is this all about? And we're going to talk about what it is. All right, this is not noise. This is real. And the question is, what is it that puts this real fluctuation in the sky? These are fluctuations you're seeing, and you want to understand what they are. All right, so this is evidence that the universe underwent an inflationary early phase, and I'll talk about that a little later. Big Bang. The Big Bang model was fitted to various temperatures. Remember last time I said that this is like a symphony orchestra where a violin playing the same note as a flute does not have the same overtones. And you can tell the difference between a violin and a flute. The violin and the flute will have the fundamental wave, now written as 2 degrees. The fundamental wave matches because they've tuned them so they match. You say it's in that's what they do at the beginning of a concert. They're tuning it so that they match. But a flute's a flute, and a violin's a violin. Even if they match in a fundamental wave, they don't match in all the higher frequencies, which is what you use to determine the sound of being a flute or a violin. This signal is all those bumps and wiggles are used by the following. We look at this map and you conclude that the geometry of the universe is flat. Flat meaning that the geometry is very simple. Of the three types of geometry, flat, closed, or open, it turns out to be flat. And that is determined by the what angular scale is that peak at. All right. You also determine the amount of baryons in the universe. This turns out to be 4.4 degrees, 4.4% of the critical density. And that is actually the abundance. That density is exactly the abundance you need to calculate the deuterium abundance in the universe and get it exactly right. So we have the ability to check the deuterium abundance. A completely different method gives us the ability to check that something is right. Independent check of predictions of the Big Bang, and they give exactly the same answer. And that is incredible that that's possible. Flat geometry and less matter than you need to make a critical universe implies something called dark energy, and we'll talk a little more about that next time. All right, and that is in agreement with the other observations. So that is good. The age of the universe, 13.7 years, and that comes out of this as well. All right, now thermal history of the universe. The thing about the photons is that they are incredibly numerous. The photons that make up this 2.7 degree background, that may seem very small to you, but it outnumbers the protons in the universe by a ratio of 10 to the 9th times. 10 to the 9th or 10 to the 10th times. That tells us that the proton is not a big deal in the universe. The photon to proton ratio not only is it 10 to the 9th, that's a pure number, and it does not change as the universe expands. As the universe is smaller, everything goes up as you decrease it. As it gets larger, it goes down. But the ratio of photons to protons is fixed. Why is it fixed at that value? A fundamental question. Okay. The photons emitted by stars and quasars and everything, they amount to nothing. The photons in the universe are all those photons in the Big Bang. All the photons that make up the light that we see is negligible. It doesn't matter. For this photon C is incredibly powerful. All right, and for that reason, it's called a hot Big Bang, because the ratio is as high as it is. If the universe were a tepid Big Bang, you'd have a number like 10 to the 4th for the photon to proton ratio. But it's hot because of this ratio. All right, I told you already about the abundance. Both the particles of photons and atoms, or any particle, scale as r to the minus 3. All right. Why is this number 10 to the 9th? And what sets this parameter incredibly fundamental? Why is it at that number? All right. Okay. The mass density of the universe was important. Radiation, blah, 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 blah. Let me skip this. All right, now let's talk about the photon to atom ratio. This is incredible. The hot Big Bang model is incredibly strongly supported. Now, this idea of the elements made in the Big Bang model dates back to the 1940s when George Gamow was working on it. And he thought that in the early universe, all the elements were made. He didn't know anything about nucleosynthesis in stars. He wanted to make everything in the universe at the Big Bang. And he calculated all this, and he got stuck. He couldn't seem to make anything heavier than lithium. He tried, and it just didn't work, so he gave up. He gave up because it didn't seem like the model worked, and he didn't know what the answer was. He didn't know anything about the nucleosynthesis in stars. All right. All types of particles exist in the early universe, and as the universe expands, these particles disappear. Okay. What we're talking about is proton plus neutron collides and makes a deuterium nucleus plus neutrino plus photons. All right. Deuterium then collides and mostly makes helium-3 and helium-4. This is all explained in this magnificent book that I recommend everybody read called The First 3 Minutes. And it's all about the first 3 minutes of the universe by Steven Weinberg, who won the Nobel Prize after he wrote this book. Yeah. All right. This is incredible. The remarkable story of how all this is made, agreeing perfectly with all the observations. And it's astounding that it works as well as it does, but it does. Deuterium, it works to make stars, destroy it. They don't create it. Okay, you can calculate, this is a famous plot that shows the deuterium abundance, shows the abundance of anything. Here is abundance shown on the vertical axis, and on the horizontal axis is the density of normal matter relative to other stuff, and the dark area is the 4.4 degrees. That is the area that works. 4.4 degrees happens to be where deuterium, that's this one here, the last one, deuterium has a abundance, and people have calculated this as a function of the abundance. They weren't sure what the abundance was, but the observations are right there, and they tell us, okay, that's what we see. The helium-3 follows this curve, and lithium-7 follows this curve. Helium-3 is very hard to observe, so I won't quote that. But lithium is exactly as the theory predicts. And this is the same interpretation as given to the microwave background. Completely different technique, also predicts 4.4 degrees. This abundance said, look, if we're going to predict the right amount of deuterium in the universe, and it has to come out 10 to the minus fifth, that's right here, between 10 to the minus sixth and 10 to the minus fourth. Right here you are. That's what we observe around the Earth and elsewhere. And that puts it right there. And it is now observed. You can observe this, and you get these incredible values. All right. Okay. All right, the density, in total density of the universe, when we play this game. It turns out to be 30%. And it's not 4% that we see. It's 30%. And so the question is, what's that? What is this density of the universe? And it's way outnumbering the ordinary matter. And this is what goes into something we call the WIMPs, the weakly interacting massive particles. This is the dark matter around galaxies. All right, this matches the theory and observations. It's just totally wonderful. All right, so the Big Bang has amazing confirmations. Yet, it's not enough. It does not predict all the elements. Gamow tried to make them all, but he couldn't make anything heavier than lithium. The density of the nuclei was too low. It just didn't work. The proposal of Big Bang nucleosynthesis was given up in the 50s. They just gave up on it because they said it does not predict the heavy elements, therefore it can't be right. The scientists had not realized. At that time, they had not realized the role of stars to making the heavier elements. But they had calculated the abundance of all the elements through lithium. And that was right. Okay, so finally it's realized they're all synthesized by fusion. The temperature is low, and the density is of a star. The temperature might only be 10 million degrees versus 1 billion degrees for the early universe. But the density of matter is very high. It's 100 grams per cubic centimeter in the center of a star, as opposed to incredible low density, 20 micrograms, that's 10 to the minus 6 grams per cubic centimeter. And that's the density of the universe at the time it was 1 billion degrees in an early universe. So it's not right to make the elements then. All right. Now, what's wrong with the Big Bang model? Okay, so far I've told you all these successes of the Big Bang model, but it doesn't work. There are certain things it does not work for. It fails. And this is something that's attracted your attention because everybody wants to find the end of the theory. They want to find where the theory fails. Where does this theory fail? Prior to 1930, 1980, cosmologists talked about 3 failure points of the theory. Here was the theory. Here's a failure point. It did not explain where all the structure came from in our universe. All the structure and all the galaxies that are made up. Where does that come from? It's not random. What made that? No explanation. It did not explain why the Big Bang was so smooth. Why does everything look the same here as here? Everything is isotropic and homogeneous to a very good degree. Why is that? It never explained why the density of the universe is almost critical. It's close to being just enough to make it go forever. And how does that work? These mysteries were through and through. As I was a graduate student in the early 70s, we debated this and basically we said that's the will of God. Because if you say it's the will of God, that means it's out of your hands. God did it. Just leave it at that. And it was so far from an explanation, we had no idea what was going on. And with no idea, you have no way to go. We didn't understand how to turn to anything. And we were very, very mystified. And then it turned out, in the 1980s, there's somebody who we're going to meet next Tuesday, Not really. But an individual named Alan Guth came up with the theory, but he wasn't worried about these cosmological difficulties. He was worried about something called monopoles. And he was wondering why the universe didn't have so many monopoles that dominated us. And he didn't know what they were. And we'll talk about that on Tuesday. All right, that is the end of the lecture. And you should be sure you come to class. I'm going to really explain everything. The whole universe is going to be explained on Tuesday. Okay, so come and meet, and I'll tell you about it. Okay.